Okay, thanks for the introduction. And yes, this is work that I did during my PhD. And yeah, today I'll be talking about eventually sound points to analysis. So as a motivating example, we're going to consider Android malware detection, and in particular, using a static taint analysis to try to identify source-to-sink taint flows that are characteristic of potentially malicious behaviors in Android apps. And in particular, this static taint analysis is going to be an example of a client for the eventually sound points to analysis that I'm going to describe. So basically, what's going to happen is we're going to take an Android app that we want to check, determine whether it's malicious, and we're going to take that app code together with the relevant portions of the Android framework code, and we're going to feed it to our static taint analysis, which is going to output a list of source sink flows which correspond to potentially malicious behaviors, and these can then be sent to a security analyst to determine whether or not the app is malicious. So this is great in theory, but in practice it turns out that analyzing the Android framework source code can be really challenging. So it makes use of a lot of hard to analyze language features, including things like native code and Java reflection. And these, if you're trying to handle these soundly, then that can introduce a lot of imprecision into the static analysis. So in practice, a common solution is to actually omit analyzing the Android framework code and instead require that the user provide specifications that summarize the relevant behaviors of the Android framework code. And now we can analyze the specifications in place of the framework code, and we can get all of our results as before. The problem is that specifications are often quite expensive and time-consuming to write, and they have to be manually produced. So instead, in practice, the user will typically just write specifications as needed. So they'll look at the apps in question and try to write specifications for all of the Android classes that are relevant to finding taint flows in these apps. And then the analysis, to make sure, to maintain high precision, is going to pretend like is going to optimistically assume that the missing specifications are no-ops, which can lead to unsoundness in the outputs. So we might fail to find some malicious behaviors if the user omits a specification for a critical framework method. So this is a problem, and our goal is to basically design an algorithm that can ensure soundness despite having missing specifications. And our approach is going to be to try to use runtime checks to ensure a dynamic notion of soundness. So of course, there's been a long history of work trying to dynamically enforce soundness by instrumenting programs and doing monitoring. So a key feature of our approach compared to prior work is that we're actually going to try to improve it's not just going to be run the static analysis and then do the instrumentation. We're actually going to have a feedback loop from the runtime information observed by our instrumentation that'll improve the soundness of the static analysis over time. So at a high level in our approach, we're going to take the Android app and the partial specifications, and we're going to run the optimistic static analysis as before, which might produce a partial list of malicious behaviors. And then, rather than give the end user the original app, we're going to insert runtime instrumentation that detects counterexamples to the optimistic assumptions that we made in step 1 in the static analysis. So if these runtime checks ever trigger, then to ensure safety, we can terminate execution of the app on the user device. But we'll also send a report to the static analysis specifying what the counterexample detected was. And then the static analysis will update itself to take into account this detected counterexample. So it'll address this unsoundness, and then it'll update the results, and eventually, and we'll just iteratively perform these steps indefinitely. So the guarantee here, so we do get a dynamic soundness guarantee by using the runtime checks. And in addition, we get this extra guarantee that eventually the static analysis results will be sound with respect to all subsequent executions. So what do I mean by that? Basically, the idea is that if you look at the sequence of executions on user devices, there are going to be reports of counterexamples early on in this sequence of executions, but we guarantee that there comes a point in time at which no future reports will ever be issued. So basically, the number of counterexamples that can ever be issued is finitely many. And practically speaking, this ensures that, this kind of suggests that over time, the number of times we have to terminate the app on the end user device goes down. And also you can use, of course, you can use beta testing and other strategies to try to further mitigate the number of reported counterexamples before you even deploy the app to end user devices. So in addition to eventual soundness, which is what I just described, we also ensure a notion of precision. The whole point of introducing specifications was to ensure precision of the static analysis. So we guarantee that our static analysis will always be at least as precise as knowing all of the specifications beforehand. So now I'm going to go into a little bit more detail of our eventually sound points to analysis. So first I'm going to give an example of a toy Android program. So on the left-hand side, I'm going to show the code for this program, and on the right-hand side, I'm going to show a pictorial representation of the taint flow in this code. So this code is going to start off by extracting the location, the user's location from the Android framework. It's going to add this information to a list. It's going to retrieve the information from the same list, and finally, it's going to leak this information outside of the system using an SMS message. So assuming we label the return value of get latitude as a location source, and we label the, the text argument of send SMS as a sensitive sync, then in principle, we can run a static taint analysis on analyzing both the Android framework and the Android app and find the source sync flow in this application. So the problem, as I mentioned before, is that it's really hard to analyze the Android framework code. So we actually want to omit analyzing it. And instead, we're going to, the user is going to provide points to specifications. And these are basically specifications that summarize the aliasing behavior induced by framework code. So in particular, the annotation alias of xy means that a variable x in the framework interface may alias a different variable y in the framework interface. So in this example program, for example, for the list class, the annotation says that the argument of the add method may alias the return value of the get method. So once we add this annotation to our system, we can analyze it in place of the Android framework and find our source sync flow as before. The problem, as I mentioned earlier, is that there are often missing specifications. And the reason is simply that it's really expensive to write specifications for the entire Android framework. There are more than 4,000 Android framework classes. A given app may use hundreds of these classes, and the framework is evolving over time. So even if you did sit down and write specifications for every method, you would still have to update it every year when Google updates the Android API. So instead, specifications are typically written as needed. And the reason this works is that for a given app, only a few of the classes are actually relevant to finding the taint flows. So it may use a lot of classes, but most of them aren't really interesting from the perspective of the static taint analysis. And in our experience, over the course of a few years, we analyzed a couple hundred apps, and we've only needed to write specifications for about 175 classes in the Android framework to find all of the interesting source sync flows in these apps. Of course, this leaves the possibility that there might be missing specifications. If there are missing specifications, for example, if the specification for the list class is missing, then we're no longer going to be able to find the source sync flow. So our approach, the eventually sound points to analysis, proceeds in 3 steps. The first step is going to be to run the optimistic static analysis. Second step is going to be monitoring for counterexamples. And the third step is going to be updating the static analysis to account for detected counterexamples. So I'm going to go through each of these steps in a bit more detail now. So first, the optimistic static analysis. It's the same thing as what I described before. So basically, we just run the static analysis where we optimistically assume that missing specifications are no ops. So in this case, we're not going to be able to find the source sync flow. The second step is to monitor for counterexamples. And we're basically going to instrument the app to try to detect missing alias edges. And for now, we're going to assume a naive instrumentation scheme where we simply instrument every program statement that's relevant to points to analysis. So this includes things like object allocations, field loads and stores, and also assignment statements. And if we instrument every statement in this way, then we publish this, this app on, we give this app to the end user who starts executing it. And if you start executing this program, the instrumentation is going to record the reference value at each program statement. And we can use this to reconstruct the dynamic points to graph. And as soon as the line 4 of the program is executed, the instrumentation is going to notice that in the program, it's actually the case that the data variable and the latitude variable are aliased because they're equal references. So that means that there's an alias edge between these two variables. Yet however, this alias edge was not present in the results of the static points to analysis due to the missing specification. So this is actually a counterexample to the optimistic assumptions. So this system is going to report this missing edge, and we're going to add the reported counterexample to the, it's going to report the missing edge to the static analysis. So now the static analysis will take this missing edge. It'll add an annotation specifying that there is this missing edge. And then now, once we've added this to the points to analysis, we can actually find the source sync flow. So once we know that latitude and data are aliased, maybe aliased, then we can find the source sync taint flow. So far I've described a naive monitoring scheme. It turns out that we can actually, so this naive monitoring scheme it ensures dynamic soundness, but it actually incurs a lot of overhead. So it's not a practical approach. So we can actually substantially optimize, substantially reduce the amount of instrumentation that's needed and still ensure dynamic soundness. So I'm not going to go through the details, but just to give a very high-level idea, if we look at this app and we continue executing it, we're going to further discover, the runtime instrumentation is going to further discover an aliasing between latitude and data dupe. But in some sense, this is a superfluous counterexample because we can derive it once we know that latitude and data are aliased. So in this sense, we actually don't need to monitor the, we don't need to record the value of data dupe since we never need to record this counterexample. And yeah, I'm not going to go into the details. You can see our paper, but basically we can use this intuition to dramatically reduce the amount of instrumentation needed. Another trick we use, which you can also see our paper for, I'm not going to go into the details of how this works, we can also generalize these counterexamples from a single app to specifications that can be used across apps. And we can use specification inference algorithms to do so. So just to summarize, the eventually sound points to analysis is going to first consist of 3 steps. Optimistic static analysis, instrumenting the app to detect counterexamples, and then updating the app to the static analysis to address the counterexamples. So I'm just going to quickly go through our evaluation. So we evaluated our approach on a benchmark of 72 Android apps. We ran each Android app in the Android emulator for an hour using Monkey to generate random events. And so first we looked at the running time, the overhead of the instrumentation. So first we considered, so here I've plotted a graph of the overheads for the apps in our benchmark. This is with no assuming that the user has not provided any specifications. As you add specifications, you can actually reduce the runtime overhead. So even now, for most part, for many of the apps, the runtime overhead is kind of acceptable, but there are a group of apps in the tail where the runtime overhead is just way too high. So as we add specifications, we can reduce the runtime overhead. very quickly. So here I've just shown the runtime overhead if we use the current specifications in the system. So there are still some outliers, and we show in the paper that if you keep adding some more specifications, about 10 to 15 more, you can get these down to reasonable levels as well. There's a similar story for data usage. This is how much data is generated by the instrumentation. And finally, we also look at the number of reported counterexamples over time, just averaged across all of the apps. And as you would expect, the frequency of reports kind of goes down over time. So what this means is that we're terminating the user app less and less frequently as time progresses, which is kind of what we would expect. So just to conclude, so far we've focused on this kind of one setting of points to analysis and the Android framework, but I think in general hard to analyze code is ubiquitous, and specifications are a really promising way to address these issues. But then missing specifications becomes a problem, and I believe that eventual soundness is a promising approach, combining dynamic information and static information in order to ensure soundness over time. So with that, thank you very much for listening, and I'll be happy to take any questions.
That was a very good talk, a lot of interesting work. Just one question. If, of course, code evolves over time. So what happens if specifications exist but become out of date? Does the system detect this, or are specifications always assumed as truth and going to run into issues at some point?
Yeah, that's a very good question. So for this work, we are assuming that they're kind of fixed. Generally, in our experience, as the Android framework gets updated, they're adding new methods rather than modifying existing code, so it's not that much of a problem. In principle, you could try to just look at what code got modified and then invalidate those specifications, but that's not something we've studied.
Very interesting talk. So here.
Thank you.
Yeah, so I have a quick question regarding, so you said you optimize the instrumentation over the Naïve approach. Do you have a number over how much overhead does it reduce?
We don't have explicit numbers in our paper, but if you look at previous papers that use the Naïve instrumentation scheme on similar benchmarks for Android, they incur, I think, about 20x overhead, so whereas ours are like 20%, so it's a huge difference. Yeah.
Other questions? I'll get who we didn't get before.
So it sounds like we're doing a kind of counterexample guided abstraction refinement, essentially, except the counterexamples are coming from the users rather than being generated by a tool. So a common problem in that area is that your abstraction gets refined and refined and refined, but never actually becomes precise enough. But you have a guarantee, you say, that your analysis eventually always becomes completely sound. Could you explain how that originates in your system?
Right, so we're not, I don't think the analogy is exactly right, because we're not actually refining the abstraction, we're simply discovering unreported or previously unknown aliasing relationships. And basically the guarantee comes from the fact that there's only a finite number of possible aliasing relationships in the program. So you can't kind of add aliasing relationships indefinitely.
Sure, thanks.
Let's take one final quick question and set up for the next session. We can switch laptops. We'll take the final question. If Jan wants to connect. I think we're connected right away.
Okay, so my question is when you are looking for these missing edges, do you account for anything that will alias between two framework methods, or are you only looking for an actual taint flow in the counterexample?
It's not guided by the taint flow. So it is restricted to look for edges that, so we do kind of consider the space of possible missing points to edges, all possible missing points to edges, and we only monitor for those ones. But right now it's not client guided, but that would be an interesting optimization to consider. Okay.
Okay, thank you, Osbert. Let's thank the speaker again, and this concludes.